10 septillion years. That's a 1 followed by 25 zeros. This amount of time might seem like eternity to many people. After all, the age of the universe is only about 13.8 billion years. But to a quantum computer, this might be just 5 minutes. Recently, the release of Google's quantum chip Willow has caused a stir in the tech world. You might have heard of quantum computing, but it seems too distant for most. However, Google's Willow chip might revolutionize our understanding. Today, let's talk about it. Before introducing the Willow chip, let's first briefly understand the basic concept of quantum computing. Quantum computing is a new type of computation based on the principles of quantum mechanics. It is fundamentally different from traditional computers. Traditional computers use binary digits, which are bits. Each bit can only represent 0 or 1, just like a switch that can either be on or off. In quantum computing, the basic unit is the quantum bit, or qubit. It can use quantum states to represent and store information. Quantum states are quite magical. They can be a mix of both 0 and 1. This means that a quantum bit can represent multiple states at once. This property makes quantum computers particularly suited for solving certain complex problems. For example, imagine we need to find the exit in a huge maze. A traditional computer might need to try every path one by one until it finds the exit. A quantum computer, on the other hand, can consider all possible paths at once, like sending out countless avatars, each exploring a different path. Once one avatar finds the exit, the entire computation is completed. This is the power of quantum computing's parallel processing. It can process massive amounts of information in a short time, whereas a traditional computer might take an unimaginably long time. However, quantum bits are very fragile. They are easily disturbed by the outside environment, which can lead to computational errors. Additionally, as the number of quantum bits increases, the difficulty of control and error correction grows exponentially. Therefore, how to effectively protect quantum bits and reduce error rates has always been a huge challenge in the field of quantum computing. The reason Google's Willow chip has attracted attention is because of its remarkable achievements in quantum error correction. As the number of quantum bits increases, the error rate of Willow decreases exponentially. Specifically, to validate Willow's quantum error correction capabilities, Google's research team tested various scales of physical quantum bit arrays. Each array forms a D by D quantum bit grid, known as a surface code. Each surface code represents a coded or logical quantum bit. In Willow, researchers expanded the surface code's distance from 3 by 3 to 5 by 5, then to 7 by 7. With each expansion, the error rate decreased by a factor of 2.14. This exponential reduction in error rate is referred to as below threshold in the quantum computing field, which is a milestone achievement. Additionally, the lifetime of logical quantum bits in Willow is much longer than that of the quantum bits that make them up, reaching 2.4 plus or minus 0.3 times. Since Peter Shor introduced the concept of quantum error correction in 1995, this has been a goal pursued by scientists. Now, this breakthrough shows that Google has taken a key step toward building large-scale, practical quantum computers. In addition to breakthroughs in quantum error correction, Willow also demonstrated incredible computational power in benchmark tests. It can complete a standard computation in less than 5 minutes, whereas the fastest supercomputer today, Frontier, would require over 10 to the power of 25 years to complete the same task under optimal conditions. If you write this number out, it is a 1 followed by 25 zeros. This is such an enormous time span that it's hard for us to comprehend with conventional thinking, especially since it far exceeds the universe's age of approximately 13.8 billion years. To test Willow's performance, Google used random circuit sampling, RCS, as a benchmark, which is one of the most difficult classical benchmarks achievable on a quantum computer. This test serves as a crucial standard for evaluating quantum computer capabilities. Any team building a quantum computer would want to beat traditional computers in this test, because only by doing so can we prove that quantum computers have a real advantage when handling complex tasks. Google has consistently used this benchmark to evaluate the progress of its quantum chips. This allows us to clearly see the continuous improvement in quantum computing capabilities, from the previous Sycamore chip to the current Willow chip. The Willow chip now has 105 quantum bits, which gives it greater capacity to handle complex computing tasks. Compared to Google's previous Sycamore chip, the Willow chip shows significant improvements in several areas. For instance, its T1 time, which is the time quantum bits can remain in an excited state, is now close to 100 microseconds, approximately 5 times longer than the previous generation chip. The chip's components, such as single-qubit gates, two-qubit gates, qubit resets, and readouts, have all been carefully designed and highly integrated. In terms of manufacturing, the Willow chip is produced at Google's state-of-the-art facility in Santa Barbara, California. This facility is one of the few in the world built from the ground up specifically for quantum chip manufacturing. It features advanced equipment and technology, ensuring the high-quality production of the chips. During the manufacturing of the Willow chip, Google paid close attention to every detail, striving to achieve the highest performance and reliability from chip design to process optimization. The performance of the Willow chip in the RCS benchmark test not only demonstrated its significant advantage in computational speed, but also sparked deep discussions about the nature of quantum computing. Its computation speed is so fast that some scientists have even started speculating whether quantum computing might involve collaborative computation across multiple parallel universes. Google's official blog mentions that the computational power of the Willow chip is so powerful that its processes might involve the concept of quantum computing occurring in many parallel universes. This aligns with David Deutsch's prediction of a multiverse in which we live. In fact, two individuals may be the most important or pivotal figures in the history of quantum computing: Richard Feynman and David Deutsch. In 1981, during a famous lecture on the future of simulating physics, Feynman made an important point. If you want to simulate nature, you'd better use the laws of nature to do the simulation. He discovered that classical computers struggle to simulate the behavior of quantum systems because of the vast amounts of superposition states and quantum entanglement in quantum systems. When simulating these superposition states, the computational load increases exponentially with the number of particles involved. Therefore, to simulate quantum systems, you must use a quantum system for the computation. Although Feynman introduced the idea of quantum computing, he didn't propose how to build a real quantum computer. In 1985, David Deutsch published a famous paper titled Quantum Theory, the Church-Turing Principle, and the Universal Quantum Computer, where he first proposed the universal quantum computer model. Deutsch's goal was to build a universal quantum computer, just as classical computers are based on the Turing machine. He wanted to define a similar mathematical model for quantum computers. He also introduced important concepts like quantum bits and quantum gates. Crucially, Deutsch not only constructed a theoretical model for quantum computers, but also believed that the working principles of quantum computers are closely related to the parallel worlds interpretation. In his view, the parallel computing ability of quantum computers arises from the coordinated computation of multiple parallel worlds. However, according to Deutsch himself, the quantum computer was merely a byproduct of his effort to prove the existence of parallel worlds or the multiverse. Of course, the concept of parallel universes remains widely debated within the scientific community. Some online commentators believe that the claims made in the official blog might be exaggerated, while other scientists have pointed out that the complexity and wonder of quantum computing mean that we cannot rule out such possibilities and further research and exploration are necessary. Let's take a look at Google's history in quantum computing. As early as 2012, Google, under the leadership of Dr. Hartmut Neven, established the Quantum Artificial Intelligence team and began working on building a practical, large-scale quantum computer. Neven had proposed what he called Neven's law, which states that the speed at which quantum computers solve certain problems would increase exponentially, far outpacing the rate of improvement in classical computers, as predicted by Moore's law. At the time, Google was essentially starting from scratch in the field of quantum computing. In 2014, John Martinis, a fellow of the American Physical Society, joined Google as the chief scientist for quantum hardware. His arrival provided strong technical support for Google's quantum hardware research. In 2019, Google achieved quantum supremacy for the first time. The Sycamore quantum processor they developed demonstrated computational power far exceeding that of traditional supercomputers when solving a specific problem. Although the Sycamore chip only had 53 qubits, it completed a task that would have taken a supercomputer 10,000 years in just 200 seconds, an extraordinary achievement at the time. From 2019 to 2024, Google's quantum computing team continued their efforts, constantly improving the performance of quantum chips through ongoing research in areas such as quantum error correction, qubit stability, and computation speed. After years of hard work, they finally introduced the Willow chip, which surpassed the Sycamore chip in multiple areas, marking another significant milestone in Google's quantum computing research. The breakthrough with the Willow quantum computing chip initially shocked many cryptocurrency investors, including those involved with Bitcoin and other cryptocurrencies. Currently, the security of cryptocurrencies primarily relies on mathematical problems in cryptography, such as elliptic curve cryptography, ECC, and RSA encryption. These algorithms are based on the assumption that, given current computational capabilities, it is not feasible to break the algorithms within a reasonable timeframe. However, the advent of quantum computers disrupts this assumption. Quantum computers can run a quantum algorithm called Shor's algorithm, which is specifically designed to break encryption based on large number factorization. In other words, the widely used ECC and RSA encryption technologies in the cryptocurrency field would become vulnerable in the presence of quantum computers. Once quantum computers reach sufficient computational power, they will be able to rapidly crack existing cryptocurrency systems, obtaining users' private keys and controlling their assets. This would lead to the collapse of current cryptocurrency networks. Currently, Google's Willow chip has only 105 qubits. Of course, if Google can further increase the number of qubits and maintain the current level of quantum error correction, breaking cryptocurrency encryption may just be a matter of time. Vitalik Buterin, the co-founder of Ethereum, has also stated that even if quantum computing makes breakthroughs, cryptocurrencies can address this issue to some extent through hard forks. However, dormant wallets would face significant risks. It should be noted that while Willow has shown impressive performance in benchmark tests, it has yet to demonstrate capabilities that surpass classical computers in practical applications. In the long term, quantum computing could spark a technological revolution that will have a profound impact on our lives. However, in the short term, the development of quantum computing still faces many challenges, such as the relatively small number of qubits and the need for further improvements in qubit stability and scalability to achieve large-scale quantum computing. Although some progress has been made in quantum error correction, it still needs continuous refinement to ensure the accuracy of quantum computing. Additionally, the cost of quantum computing is extremely high. To achieve commercialization, costs need to be reduced and cost effectiveness must be improved. Despite these challenges, the success of Google's Willow chip still demonstrates the vast potential of quantum computing. With ongoing technological advancements and continued investment from governments and enterprises around the world, probably in the near future, quantum computing will gradually enter our daily lives and provide new solutions to solve various complex problems.